All right. Good evening, everyone. Thanks for showing up to our last Monday meet session.
Wow.
I'm sure you're all excited.
That's what I'm saying. Ooh, I'm with you, Leroy.
Yeah, it's mixed emotions here.
Yeah.
Doc, we could use you all the way down to the week 6.
You'll be fine. You'll be fine. All right. So let's get started. This week, we're going to transition from discrete random variables, which remember are things that are counted, to continuous random variables, which are things that are measured. And that's really the big difference between the two. And that's really what I want you guys to always be thinking about is discrete variables are counted and continuous ones are measured. And also some students really get hung up in this whole random variable thing. It's just a fancy way of saying the data that you collected is associated with a random variable, right? So if you asked everybody their heights, then the quote unquote random variable would be a person's height. And then all of the data that you collected, all the different heights from all those people, would be associated with that variable. And we call it a random variable because it's technically random as to every data value you get, because you're technically asking a random person for their height. So therefore their height becomes random. So that's what this whole random variable thing is. But from a practical standpoint, just envision that we're talking about data, right? We're talking about data that you get from a survey or from an experiment or whatever, but these random variables are just the questions on a survey that get you data, right? Or the experiment that you run that gets you data. That's all it is. All right. So the big difference between continuous random variables and discrete random variables is that discrete random variables have a finite number of possibilities. And those answers, right, those data values are always integer values because, again, they come from counting something. How many siblings do you have? How many televisions do you have in the house? How many times a week do you eat at a fast food restaurant, right? Those types of things, they will all have a finite number of answers because even if you go, those crazy families that have 19, 20 kids, there's still an upper bound to how many siblings you have. There's a maximum number of times you can eat out in a week. Even if you're eating 5 meals a day for 7, it's not going to get any more than 35, those types of things. So they will all have a finite number of answers, whereas a continuous random variable, something that is measured, will have infinitely many values because you have every single possible number all along the number line, right? Somebody could be 64 inches tall, but they could be 64.1 or 64.001 or 64.0001, right? And so you get all these infinite measurements, and so you get infinite values. So some typical examples that I've talked about before: heights and weights, right? Length of time of a particular, right? Any time is always a measurement. So any length of time, whether it's for a particular product or whatever, and then also because your age is technically just a length of time, your age becomes a continuous random variable. Even though most of these things, if you surveyed people, instead of actually taking somebody and measuring their height and measuring their weight with a scale, and you ask them just to report their height and weight, and same thing with their age, of course all three of those are going to get integer values, right? Everybody's going to give you their height, their weight, and their age in whole numbers. They're not going to tell you I'm 6'4.2 inches, that type of thing. They're just going to say I'm 6'4", right? Or I'm 5'10", and I don't weigh 253.68 pounds. It's I weigh 253 pounds. It's that kind of thing. I'm not 48 years, 6 months, 2 weeks, 3 days, and 5 hours old. I'm 43. It's those kind of things. So even though the data you collect is going to seem discrete on the surface because all of the values are just going to be nice, pretty little integers, does not mean that the data itself, the entire population of data isn't actually continuous, because it is. You're just getting, well, technically you're getting falsely reported data because everybody is just self-reporting their stuff, and it's all been rounded. So it's not really false, but you get the idea that it's all been rounded, right? So when you have a continuous random variable, what happens is when you start plotting values, remember we used to plot histograms. We would have, in all these previous homework problems, we had all these histograms, or we can make this nice little histogram showing frequencies of data in different categories. First, we had bar graphs for when we had discrete categories, and then we saw those again when we did the binomial distribution, where you could have a bar graph, because again, binomial went back to discrete values where you had 0 successes, 1 success, 2, 3, 4, all the way up to however many, how big your sample size was, and you have an individual bar showing the probability of each of those successes happening. Well, we also saw some examples before where we had continuous data. Remember, we had data that had decimals and all this kind of stuff. And what we did is we put them in bins, and we said, okay, here's a bar graph that shows this bin, and here's a bar graph that shows that bin. I'm sure you guys all remember back from, I think it was this maybe week 2, when we had that whole problem where we were supposed to create a histogram, and we had to create 7 classes, right? It had to start at like 0.705, and it was, like 0.35 wide or whatever it was, right? Well, that's taking continuous data and putting it in bins so you can make these little histogram bars. Now, if you can think about, and some of you even did this, as you gave it more and more bins, the bins got thinner and thinner and thinner, and you got more and more of these little individual bars, right? And the idea is, take that out to infinity and have an infinite number of bins, i.e. an infinite number of those little bars. And what happens is the width of each bin shrinks down to nothing, and you get basically just a straight line kind of thing. And instead of having all these little boxes, you get a nice smooth curve. And that's where we get the normal curve, or a skewed normal curve, right? So what's happened here is all these little bars in this histogram have gotten thinner and thinner and thinner and thinner and thinner until you get a smooth curve out of it. And just like every other probability distribution, the area inside all of those bars added up to 1. Well, the area inside this curve has to add up to 1, because again, height and then width, when you put that together and gives you area, that's supposed to represent the probability of something happening. And so the area under any of these continuous random variable curves will always have a total area of exactly 1, because we know probabilities add up to 1. So here are those properties that I've already talked about, right? We know the area under the curve is equal to 1. We know that if we want to find the probability of any event, we can no longer ask what's the probability that x equals 3. That answer is always 0, because the area for x equals 3 is 0, because the range, right? You have to have a range in order to have an area. Because if we think back to this picture, if you thought about x being 3, there would just be a vertical line above 3, and it has no width, so therefore it has no area. The only way we can now answer these questions is to think of a range for x and say, okay, so now what's the probability that x is between 2.9 and 3.1? We can kind of, fudge it a little bit if we're still trying to figure out the probability that it equals 3. And we can make that smaller and smaller. We can go, okay, 2.99 and 3.01 and those kinds of things. But you're still getting an actual range. And that range gives you an area because it gives you a width. So all of your probability questions for continuous random variables are going to be, what's the probability that something is less than a value, greater than a value, or in between those two values? And when I say less than, greater than, it's also the same thing to say less than or equal to, or greater than or equal to. So you could always swap these symbols for just the strictly less thans, right? You can get rid of the equals because it doesn't change anything. Because remember, equaling a number is 0. So for instance, if you said, what's, if we put in, let's say 5 and 10 and left these symbols, we got an answer of 25%. If we change these two symbols to strictly greater than and strictly less than and got rid of the little equals and still ran it between 5 and 10, we would get the exact same answer as of 25%, because the equals doesn't make any difference, because x equaling a is 0 and x equaling b is 0. So adding in that little equals part doesn't make any difference. And so visually, this is what you're getting. You can see down here, the picture has the strictly less than. And this area would be the exact same area as the inequalities with the equal portion on there. So as I've said, there's no probability of something equaling a specific number. So we can no longer ask what's the probability that x equals 5 or x equals 4 like we had in the previous week's homeworks. We do have simple SAS code to run all these for us, right? Instead of the binomial, it's just the normal. Instead of having the sample size, the probability of a success, and the number of successes, we have the value that we're looking for. So that's kind of like the number of successes, right? That was still our x before. But instead of sample size and probability, we have the mean and the standard deviation. And then we run a CDF, because there is no PDF for a normal. So it's always the cumulative density function. And this does just like what all the other CDFs do. This always gives you the area to the left of x. So it's everything less than or equal to x. So if you need to find things that are above x, obviously you got to do 1 minus that. And if you need to find the area in between two things, then you have to run 2 of them and do a subtraction. And I always say that the best thing to do is to draw yourself a picture so you can figure out what the hell you're trying to find. And then it'll help you figure out, okay, am I doing 1 minus? Am I doing 2 of them and subtracting? Or am I doing just a normal one? Because those are the only 3 options, right? If it's a less than, you just do a normal CDF. If it's a greater than, you do 1 minus the CDF. If it's an in between A and B, you simply do a CDF of A, a CDF of B, and take the bigger one and subtract the smaller one from it. And then that gives you the area in between. So those are the only 3 scenarios you'll ever have. Okay, the standard normal distribution is a very special version of the normal distribution that has been standardized. Basically, what we've done is we've taken any set of data that has a normal distribution, and we have divided every single data value by the mean. So if the mean was, let's say, 17.5, you would take every single data value in your data set and you would divide it by 17.5. And what that does is it just shifts the entire distribution 17.5 points to the left, because now everything, sorry, you don't divide by 17.5. I'm a moron. You subtract everything by 17.5. So it shifts it to the left, that 17.5 points. And now your average becomes 0. So the standard normal always has an average of 0. We basically want to take that normal curve and we want to shift it so that it's centered right there on the origin on the number line. It's the middle of it, where that's the average. Average is always right in the middle. We want it to be centered right on 0. So you can very easily do that by taking every data value and subtracting the mean from it. And then that gives you an average. It gives you a whole new set of data, and that new set of data would have an average of 0. Then the other thing you can do is you can basically rename the standard deviation. It's kind of similar to 12 inches becomes 1 foot, right? And 3 feet becomes 1 yard. Or for those of you that live in the rest of the world, 100 centimeters becomes 1 meter. You can always change the unit of measure. So what you do is, if your standard deviation of your original data was, let's say, 2.3, then you now just say, okay, I'm just going to call that a 1. We're going to change the standard deviation to 1. And then that becomes your new standard normal distribution, where the mean is 0 and the standard deviation is 1. So you can apply this idea to any set of data. You're basically, quote unquote, normalizing you're standardizing your data to get this standard normal. So the standard normal distribution is called the Z distribution. And it has these beautiful properties that the mean, the median, and the mode are all exactly in the middle. So you have exactly 50% of the data above the mean and exactly 50% of the data below the mean, because the mean is the same as the median. Values of z to the left of center are always negative, and values to the right are always positive, because again, we centered it on 0. And so it makes it more intuitive. When you get what are called a z-score, when you get a z-score of 1, that means you're exactly 1 standard deviation above the middle, exactly 1 standard deviation above the mean. And if you get a z-score of negative 1.3, then you know you're exactly 1.3 standard deviations below the mean. So that's the other nice thing about putting it on 0 is it's intuitive, right? The positive z-scores tell us we're above, and negative z-scores tell us we're below. And like any probability distribution, we still have the total area is equal to 1. So as I said, we can do this in SAS very easily. Here would be a simple example where we want to basically figure out if we have a z-score of 1.36, because this x has now become a z-score because we're using the standard normal, mean of 0, standard deviation of 1. If we do the CDF, this is going to give us all of the area to the left of 1.36 as a z-score. So again, you should draw this picture. Now, you don't have to worry about how accurate, exactly where you place the 1.36. The idea is you should just know that, 0 is in the middle. So 1.36 is above 0. You're looking for all of the area below it. So this tells you that you at least know that the area has to be bigger than a half, because we know at 0, everything to the left is a half. So we have more than a half. So when you get an answer that is smaller than a half, you know, oh crap, I've screwed something up. Here, of course, we got the correct answer of 0.9. So that means there's 91, a little bit more than 91% of the data is below this 1.36. And if you guys remember the empirical rule at all, this all correlates back to the empirical rule. Remember, if we go 1 standard deviation in both directions, that captures 68% of our data. And if we go 2 standard deviations in both directions, that's 90% of our data. So if you think about going 1 standard deviation, and that's 68%, right? Well, half of 68 is 34, right? So that basically gives us 34% above, 34% below. But below, if we take all of it, is 50. So plus that 34, that's 84%. So if we're at a z-score of 1, we already have 84% of the data below us. It's that half of 64, half of that 68, which is 34, plus the other 50% below it. So to be 1.36, a little bit more than 1 standard deviation, makes sense that we're a little bit more than that 84%. And again, all those numbers will make more sense if you just draw your own little normal curve and start labeling everything, and you can see how all this stuff adds up very easily. And then, as I said, if you need to find greater than, then you just do 1 minus. And that gives you the other stuff. Now, you can always put that into your code, right? You could put 1 minus, right? You can do probability equals 1 minus the CDF, and then it'll give you the area above your X. To get the area in between, as I said, you have to basically run it twice and then subtract the 2 answers. So you would first run it with the 1.36 and get the 0.9131. You would run it again with the negative 1.2, and that would give you the 0.1151. And then you'd, in a calculator, take the difference and see that you get basically 80% in between the two. Here's another typical example. Not going to waste a lot of time on this, right? It's pretty simple. Same thing. There's got to be one with a set of, so we have a package. Yeah, all these are the same. Okay, there's a normal approximation to the binomial that is really more of a teaching tool. It's not something that we do in the real world, because the only reason why this exists is way back, well, I mean, really as little as 30 years ago, we really didn't have computer computational power to allow us to compute large binomials efficiently. You know, you would need the old Cray computer that, you know, takes an entire warehouse to do a very large binomial. But you could do a normal approximation of the binomial, and calculating probabilities on the normal curve are so easy that we actually have tables that can figure them out. And it's something that can be done by hand very easily. So this was used to approximate very complex large binomials that we couldn't do because of the limited computational powers. But, you know, as we all know, in today's modern age, you all have a computer on your phone that is more powerful than the old Cray computer was that took an entire warehouse. So we can actually compute any binomials that we need very easily, as we saw with SAS. So this is no longer something that needs to be done, and it's really just left over as a teaching tool to kind of remind ourselves that if you have a large enough binomial so that all those little bars, there's enough of them that they kind of smooth out, then you can get a fairly decent approximation from the normal curve. So as I said, this only works when n is large and p is not too close to 0 or 1. So what you have to do is you have to check some things to make sure that they sit within the parameters. We've already talked about that we know that the mean of a binomial is when you do n times p. We didn't talk about the variance, however, but that's simply just npq. And then, of course, if you take the square root of it, that gives you the standard deviation. So that's how you can get the mean and the standard deviation very easily, which is what you need in order to run the normal. Because remember, in the normal, you need to know the mean and the standard deviation. Well, this only works when n times p is relatively large. It has to be above 10, I think, if I remember correctly. And the other thing we have to worry about is that when we're trying to approximate the binomial, we have to do what's called this continuity correction, where if you're trying to find the probability that x is less than 4, you don't want to take the normal curve and go less than 4, because you're missing half of that that last bar that counts basically 3, right? Because you only want 3 and below. So what you want to do is you adjust it to be 3.5, and if you want to be greater than 4, then you adjust it up to 4.5. The idea is, right, we know that binomially speaking, if we want something less than 4, we just want 0, 1, 2, and 3. So a lot of people think, well, then shouldn't I set the normal curve at 3? No, because remember, at 3 doesn't really count 3 because equal doesn't matter. And if you put it at 4, then you're getting half of the bar, that little bar that from a binomial. You're getting half of this little bar for 4. Now, obviously, this isn't where 4 is. It's way down here, but you can't see it. But you get the idea. So what you do is you adjust it down and you let the normal start at 3.5. So that counts all of 3, but it doesn't give you any of the bar for 4. And then the same thing, if you want to be greater than 4, we know that we need 5 and above. And because we need 5 and above, we have to back it down to 4.5. So what I always say is, whatever the binomial question is, whether it's a less than, a greater than, a less than or equal to, or greater than or equal to, always figure out what your end number is. So for instance, less than 4 means we went 0 up to 3. We ended at 3. Greater than 4 means we started at 5 and went up to whatever the maximum sample size. So our end number was 5. So we have an end number of 3 and end number 5. Once you know that end number, then you need to adjust so that you include that number, right? So if we're going 3 and below in the first one, then our normal curve has to go 3.5. If we're going 5 and above, then we adjust it down to 4.5 to capture that last bar. It's a little tricky, but you have to do that in order to get an answer that's actually close. And you'll see from the homework, there's a question that asks you to do it without the correction and with the correction. And you'll see that once you do the correction, you get a much more accurate approximation. But again, as I said, we don't really do this in the real world. It's just a teaching tool because we can now do all these things, for real. We can just do the binomial. Okay, the last most important thing that we learned this week is the central limit theorem. And all this does is it tells us that, so far, all of these questions we've been talking about with the normal curve, where we've been asking, what's the probability that X is less than 10? What's the probability that X is between 7 and 8? What's the probability that X is greater than 305? Whatever the question is, it's always been based on the premise of sampling one thing, right? Go out and pick one person at random. What's the probability that their height is above 6 foot, right? Go out and sample one person at random. What's the probability that they weigh less than 100 pounds? Those types of things. Well, what happens if you want to say, okay, let's go grab 10 people at random. What's the probability that the average height of those 10 people is still above 6 foot? Or grab 10 people, what's the probability that the average weight of those 10 people is still less than 100? Now, hopefully you're already starting to think, okay, if being taller than 6 feet is, kind of abnormal, it's on the high end of the scale. And if the probability of finding one person above 6 feet, was, let's say, 20%, then wouldn't you imagine that finding 10 people who have an average height that's still above 6 feet, shouldn't that be less? Shouldn't it be harder to find 10? And it is. Same thing if an adult who, we're picking adults, if an adult weighing less than 100 pounds is rare, which it is, as we all know, then finding 10 adults with an average weight less than 100 pounds would be even more rare, right? So that probability would be even smaller. Well, exactly how much smaller? It's very simple. The central limit theorem tells us it's exactly the square root of n smaller. Now, that's not what the answer is going to be, but that's what happens to the curve. The curve tightens up and the standard deviation gets smaller. So all you have to do is, when you're running this question, instead of using the mean and the standard deviation that you were given, the mean stays the same, but now you use a standard deviation that is just the standard deviation you were given divided by the square root of your sample size. So for my two examples, you would take whatever this standard deviation was and divide it by the square root of 10. Gives you a much smaller standard deviation. Everything gets clumped together. And now those extreme values are further out in the tail. Ergo, they have less area. Ergo, they have a smaller probability. Now, you probably don't care about all that theory and where it comes from and why it works. The bottom line is, all you have to know is that you always just take the standard deviation divided by the square root of your sample size and then run it that way. So for instance, this example, we have that tires last 20,000 miles with a standard deviation of 3,500 miles. So of course, there's our mean. And then there's our standard deviation. If we picked one tire at random and want to know the probability that, it would last less than 19,500 miles, then we would just put 19,500, we'd put 2,000, and then our standard deviation would be the 3,500, and we'd run that. But we want to know what's the probability if we pick a sample of 70, that entire sample of 70 tires would have an average lifespan of less than 19.5. Well, then we adjust it, and the new standard deviation becomes 3,500 divided by the square root of 70. And we put that here we did this in our calculator. But here's the dirty little secret that they don't show you here, is you could actually in SAS just write this exact thing, 3,500 divided by SQRT parentheses 70 close parentheses 70, and it does the math for you, and it keeps all the decimals instead of rounding to 2 decimal places. So if you want to get the most accurate answer possible, just put this line in as your standard deviation instead of doing this in your calculator and then rounding and putting the answer in. We can also ask all of these answers in reverse, like what kind of sample size do we need to get a specific probability? What measurement is in the 20th percentile, or what measurement is in the 90th percentile, right? All of those things are asking these same probability questions, but they're asking them in reverse. Instead of, hey, I scored blank on my test, what percentile does that put me in? You could say, hey, what score do I need to put me in the 90th percentile? And you can see that those are basically the same questions, but in opposite direction, right? In the first question, we have the data value, we have the X, and we can just plug it in and it'll spit out a probability. In the second example, we have the probability. We want to be in the 90th percentile. So we know we need 90% of the data below us. So that's our answer, right? We need that 90 as our probability, and we need to solve backwards for the X value that gives us that. Well, we could always, plug in all of our bits and pieces, plug in our z-score, because if we know we want to be 90%, then we can get a corresponding z-score, and we can solve algebraically for X by doing all this junk. But guess what? Technology can do it for us. Technology can work backwards for us and just find these values very simply for us. I think it's called the quantile plot, or the quantile equation. If I remember correctly, it is, here it is. Yeah, quantile. So this quantile function, you can see you give it a probability. So you give it a p-value, and just like the CDF, that's the area to the left. You give it a mean and you give it a standard deviation, and it'll spit out the answer. So for instance, if we run this right here, that tells us that for a sample that has a mean of 250 and a standard deviation of 50, a value of 207.919 is at the 20th percentile. It has 20% of the data below it. So if we wanted to know, what, so if we were thinking of these as being like test scores, and we said, okay, well, what score do we need to get to be in the 95th percentile when the average test score was 250 and the standard deviation is 50? Well, then if we run it now, you can see that we'd have to score 332.243 to be in the 95th percentile or above, obviously, right? So that's much easier than trying to do these things by hand and working backwards. But there are some questions in the homework where you're going to have to use the z-score and solve backwards. So just keep that in mind. You definitely want to have this z-score formula in your notes and know what it means. Data value, mean, standard deviation, square root of sample size, right? Those are all the bits and pieces. Okay, the last thing that you guys have to do in the homework is do tests for normality. You can do it by hand here in Excel. You can create basically a set of quantile scores, and then do a correlation, do a scatter plot between the original values and these z-scores, and that'll give you your quantile plot, which tells you you're basically checking for normality. But as we've seen before, we can do quantile plots very easily in SAS. We've done it before on a previous homework example. So, why bother? Just do it the old easy way. Okay, that's all the theory stuff for this week. Any questions on that?
Dr. McBride,
Yes, Tiffany.
can you go over, I kind of got lost. I think it's in the beginning. Can you explain, let me see what slide. It's like all the way where, yeah, where it was like, I think it's slide 3 or 4, or maybe slide 4. Okay, no. Wait.
What's the concept that you're having trouble with?
where you get your percentage between 1 and then you said equals 0.9.
This one?
Yes.
So this is just simply running something in SAS and getting an answer from SAS. What I was talking about is we know that if we have the empirical rule, right? The empirical rule tells us that here's our mean, right? This is X bar or mu, if you want to think about the mean, sits right here at a z-score of 0. That's a 0, not a 6. If we go out to 1 and -1, this whole area here is 68% of our data. If we cut that in half, because it's symmetrical, we know there's 34% here and 34% here. But more importantly, everything to the left of center equals 50% of our data, just like everything to the right of center equals 50% of our data. So if we take this 50 and add this 34, we now know that basically the probability that X is less than or equal to 1 being 1 standard deviation, is going to be roughly 84%. And we can get that just from the empirical rule. So that tells us that 1.36, which is a little bit more than 1, should definitely be bigger than 84%. And we got 91%.
Oh, okay.
So I was only pointing that out to basically as a double check to make sure that, you didn't type something in on the code and got an erroneous answer.
Okay, okay. Okay, thank you for that clarification.
No problem. Anybody else? All right, nobody else? All right, so are there any homework questions you guys want to go over?
Are there any we don't?
Well, have you actually started them?
I actually have tried all of them.
Oh, good for you.
I know, which is amazing because I'm the most non-mathy person here.
Mhm.
But the main thing that I would really like to ask to make sure I understand what I'm doing
Sure.
is like on 4.70.
Yeah.
Is that formula? Wait, let's just say I did it with the formula that is I think the binomial.
Nope, you should do the normal CDF.
Oh, I bet I did it wrong then.
So for instance, let me show you how to do the first one.
Okay, thank you.
Okay, so.
CDF, wait. Okay.
Okay, so we know we're dealing with a normal curve. So we're down here on, right, we started with the binomial,
Mm-hmm.
then we had the Poissons, and then we get down here to the lovely normal.
Mm-hmm.
We have just the regular normal here, and then we have the quantile down here. So we want this one.
Okay.
It tells us that our mean is 513. It tells us that our standard deviation is 130. And the first question is, what's the probability that's greater than 600? So 600 is our value, and it's greater than, so that means we want 1 minus the CDF.
Okay.
Because CDF is always going to be less than. So the CDF is going to give us the area less than 600. Then we subtract that from 1. It's going to give us the area greater than 600. If we run just that code, there's our answer.
Oh my God, I got it right. Okay.
Well done.
I know. I'm flabbergasted.
So that's how those are done. These are all, these are all pretty much similar questions. Part D is a little tricky, requires some some algebra, but you can see this is greater than 250, greater than 600, right? Greater than 150, greater than 700. In between two things, in between two things. So you can see these two questions are pretty much asking you to do the exact same thing. This one is asking us to go backwards, right? What score is required to be invited to join the society, i.e. to be in the top 5%. So this means you want to be in the 95th percentile, because if you're in the top 5, you've got 95% below you. So that means you're just going to be using the quantile function or the quantile code, where your p-value is going to be 95 because I put you in the 95th percentile. And then you just have to use the correct mean and standard deviation, and it tells you use the same ones from 470. Now, part B, people misinterpret this. It says, what score separates the top 75% of the population from the bottom 25% of the population? A lot of people think that's asking for two different scores, and it's not. That is one score, because, as I will show you right here, if you have a normal curve and you have, what was it, top 25, bottom 25, what's the wording? Score separates the top 75 from the bottom 25. Well, that's just one score, because right here, here's the bottom 25%, here's the top 75%, adds up to 100, right? So you're just looking for one X that has 25% below it, 75% above it. So again, you would use that same quantile function, only now your p-value would be?
Wait, 0.95?
Nope, not for that one, for this
No,
question.
not for that one, sorry. Wait.
How much area is below it? Anybody else want to help her out?
Is it 0.75?
Nope.
No, because it's the below, it's
0.25.
not the to the
There you
right.
go. Yep. Good job, Mary. Yeah, it's 0.25. It's always area to the left. That's why I want you guys to draw these pictures. It's always area to the left. So you would make it 0.25, and then that would give you the answer to that one. Let's see. The rest are pretty straightforward. Right? So here's another thing. Here's where it changes. A random sample of 20 patients are picked, and then they ask those same questions again. Greater than something, in between something, and then a percentile question. But what's the only thing that separates or makes this question different from the first two questions? Well, the fact that in the first two questions, we were picking one thing. Now we're picking a sample of 20. So all we have to do, according to the central limit theorem, is change our standard deviation to be 130 divided by the square root of 20. And as I said, you can do that in SAS. You don't have to do it in your calculator. So we could actually come down here and we could just change this to divided by SQRT 20. Now I know that these numbers are all wrong, but I'm just going to run it just to show you that you don't get an error, that it works. And there you go. So there's the standard deviation. It even presents you what the standard deviation is as a number instead of divided by the square root of 20. So basically, in our code, 130 divided by the square root of 20 is 29.0689. Okay, so you can do it that way, and you don't have to do it in a calculator and worry about rounding and all that junk. And so that'll take care of these. All you have to do is adjust the standard deviation, and then the questions are exactly the same as you did up here. You can find a between, right? You can find a greater than, just like these two and these two. And then you can find a percentile using the quantile function. And just like the other thing with the quantile function, you have to adjust the standard deviation, right? Because the quantile function also has a standard deviation in it. So you would just take that, divide by SQRT 20, right? And then Bob's your uncle. You're good to go. Okay. So that takes care of that one. Same thing. These are the same type of questions, right? Where you're going to be doing it, once, and then here's 5 measurements. So we just have to divide by the square root of 5. And then here's where you go back and do the binomial distribution. So they want you to compute the exact probabilities and then the normal approximations. So don't forget that this question requires two answers. The first answer is you find the exact probability of being less than 5 given these parameters for a binomial distribution. Then use the normal approximation to get your answer for less than 5. And they want you to use just 5. Don't do the continuity correction. So just do less than 5 on the normal and see how bad it is. Then come back, do that same normal approximation, but now do it for less than 4.5. And you'll see that it actually works. It gets better, right? It gets closer to the true value that you got from the exact probability. And why? Well, because that's the continuity correction. And then for part C, they want you to compute, again, exact probabilities and corresponding normal approximations with the continuity correction. So again, you're going to have two answers for C, just like you had two answers for part A. The exact probability, right? If you want everything between 8 and 14, remember this is strictly between, you only want 9, 10, 11, 12, and 13, right? So when you're doing the binomial CDF, you have to do the binomial CDF of 13, which will give you 0 through 13. Then you have to do the binomial CDF of 8, because that'll give you 0 through 8, and you subtract that from the 0 through 13, and that will leave you the 9 through 13 that you want. That's how you get the exact probability. Then for the normal approximations, you have to do 2 CDFs and subtract the difference, but you have to remember, okay, if I only want 9 through 13, where does my upper bound end? If I want to go up to and I want to include 13, what should my normal CDF be for the upper bound?
$14.
Nope. Remember, it's always a half.
Oh, 13.5.
You got it. And then on the low end, we only want to capture 9, right? We want 9 through 13. So what should the normal CDF be down here for the 9? It should stop at what?
8.5.
What is it?
8.5.
There you go, 8.5. So those are the continuity corrections you want to do for that one. And then the last question asks you to create a normal quantile plot, which is we've already done, and compute the correlation coefficient and p-value, which it just spits out in the technology when you run it. So that's it, guys. That's the entire homework set. Any questions on any of those? All right. So any last minute questions before we go?
I'm sorry, just real quickly, back to 4.88C. I got myself confused as you were talking. And 4C, we are doing the continuity correction. So you don't want to see the 8 and the 13. What you want to see is the 8.5 and 13.5, correct?
Yes.
Okay.
When you're doing the normal CDF, when you're doing the binomial, because you also have to get the exact probability using the binomial, you need to do 13 and 9.
Got it.
Anybody else?
I had a question about the final project next week, but I didn't want to jump into that before we were ready.
Nope, that's fine. Go for it.
On the data, and I apologize if this has been addressed already. I was just trying to read through it. On the part 3, where we're supposed to basically bring forward our own data, is that data that we can find somewhere, or like we can make it up, or we're supposed to actually collect it, or?
Yes, yes, and yes. It can be any of those 3.
Okay. Okay, cool.
Yeah. The whole point of part 3 is to get you thinking statistically about your dissertation and what kind of research question can you come up with for your dissertation that can actually be measured, right? Something that can actually have a continuous random variable. Now, if your scenario for your dissertation just does not have any measurement variables in it, whatever it is you're studying doesn't require measuring anything, then make it up. Make up a variable that is related to your dissertation that you don't care about, or make up the entire scenario from soup to nuts. But in order for this assignment to be the most beneficial for you and not just be busy work, is for you to try and make all of these things as closely related to your dissertation as possible. So try to come up with a research question from your dissertation topic that would involve measuring something. And then you can answer all of these questions based on that scenario, which will get you thinking about what you would do for your dissertation. And when you go to write up your actual dissertation, this will already give you a framework that you can just expand on when you have to do your methodologies chapter. Now, and that's for basically 1 through 5. For question 6, you're then supposed to basically create your own scenario questions from your research topic. So let's just say your research topic involved measuring people's yearly income. Then for question 6, you would say, okay, for part 1, I could try and find the probability that a household's yearly income is greater than $100,000. And for part 2, I could ask the question, what's the probability that one household's income is less than $50,000? And then for part 3, I could ask the question, what's the probability that a household's yearly income is between 90,000 and 150,000, right? Or whatever. And then for 4, I could say, okay, what household yearly income would put them in the 90th percentile? Or you could even, go put them in the 99th percentile, right? Make them the 1%ers. And that's what this question would be. And then as far as graphs to visualize your solution, well, those are just those normal curves that we saw in all of these slides, right? That's a less than, right? Let me get back up out of these. So there's an in-between curve. There's a greater than. There's a less than, right? So it'd be those kind of things. And the same thing for a percentile picture. It would just be the same kind of picture, except instead of, this being a number, this would be your X, and in here would be labeled with, 90%. I'm trying to find what value gives me 90%, that kind of thing. So that's how you would do those. And again, you would just put it into the context of your research question. But as I stated, if this doesn't fit your research at all, then all of this is going to be made up. This scenario is going to be made up. And then these questions, of course, everybody's going to make these up, but they're going to be based on this fictitious scenario. You do not have to have data for any of these, and you do not have to actually compute these questions. You just want to be able to come up with the scenario, basically write out in English what you're looking for, translate that into a probability statement, and then show a corresponding normal curve picture that would, be the thing. Now, if you want to actually do all the stuff with it, so, for instance, if you were doing the whole household income and you either had the data or just make it up and say, okay, the average household income is going to be 75,000 with a standard deviation of $5,000. Well, then based on that, you could actually compute all of these questions, and you're more than welcome to do that. But again, this is just a thought experiment. So the answers don't matter. It's the thought process and writing up all this stuff that matters. Does that clear that up a little bit, hopefully?
Yes, thank you. Also, did I imagine it, or did early on in the class, did you, because the final project says something about presenting.
Yeah, we're not doing that.
Okay. I was like, maybe that was wishful thinking, but I feel like he said that. I just wanted to clarify.
Yeah. There is no part 4. You are not presenting these in any way, shape, or form.
Okay. And then can we pre-submit the final project like we've done with the homework to get your feedback before we submit?
No.
Okay.
The training wheels come off for the final project, but there's really not much to it other than you know what? Screw it. Go ahead. Submit it early. I'll give you guys some feedback. You've got to get it into me by midnight Thursday of next week.
Okay. Thank you.
But I imagine people will have questions on this Thursday in addition to the homework. So
And
I-
the final project is due on a Saturday. It's not a Sunday.
correct. The last day of class is Saturday,
It's a
not
Saturday.
Sunday. Yeah. So it'd be better to get them to me earlier rather than later if you want any good feedback to give you time to work on it. But the best thing you could do is just go watch the old meet sessions, because I go through literally every single question in the old ones.
Thank you for being so generous, Dr. McBride.
Sure. I'm a pushover. I'm a people pleaser, as my therapist likes to tell me. All right. So that should do it, guys. Thanks for showing up. We will see you Thursday with all of your homework and final questions. That will be our last meet session. And that'll get you ready to go.
Thank you.
Yep. See you guys Thursday.
Thank you.
Good night.
Okay, Doc. See you on Thursday.
All right. Thank you. Good night.
Good night.